We're taught that water puts out fire, but in specific industrial settings, a single drop hitting a burning surface explodes into a massive fireball. Suppression removes one leg. Spray water on a typical fire, it absorbs. Fires break out. The intuitive response for first responders is to flood the area with water to achieve that exact cooling effect. But extreme limits, this basic thermodynamic model breaks down. The very tools meant to stop the fire become the mechanism that spreads it. The clearest example of this failure occurs in Class D fires. These involve combustible metals, specifically magnesium, titanium, sodium, and lithium. These materials do not burn like normal combustibles. Their baseline combustion temperature routinely exceeds 5,000 degrees Fahrenheit. You will find these specific hazards concentrated in manufacturing plants, aerospace facilities, and high-precision machining shops. In these environments, innocuous-looking piles of metal vest and machining shavings are actually highly reactive fuel sources waiting for an ignition trigger. If a fire breaks out in one of these piles, spraying it with standard agents will trigger a violent, unpredictable reaction. Recognizing a Class D risk means acknowledging a physical state where standard safety tools cross the threshold and become active threats. To understand the mechanics of how water fails, we first need to look at a Class B liquid hydrocarbon fire, where the failure is driven by thermodynamic expansion. Hydrocarbon fuels, like crude oil, are nonpolar and have a lower density than water. If you spray water into a burning oil storage tank, the two liquids do not mix. The heavier water sinks to the bottom of the tank, floating the burning oil directly on top of it. As the lighter fractions of the crude oil burn away at the surface, they create a dense 500-degree layer of hot oil. This heat wave slowly descends through the tank, moving steadily toward the trapped water at the bottom. When that 500-degree heat wave finally hits the liquid water layer, it triggers an instantaneous phase change. The water flash boils into steam. At standard atmospheric pressure, liquid water expands 1,700 times into steam. Trapped at the bottom, this massive expansion acts as a mechanical piston. It displaces the column of burning crude oil upward and outward over the walls. As the steam bubbles rise through the oil, they carry burning fuel droplets into the air. This aerosolizes the fuel, drastically increasing its surface area and maximizing oxygen exposure. The physical expansion of the water creates an explosive industrial boilover. Instead of extinguishing the flame, the water physically multiplies the combustion area. In a Class B oil fire, the water acts as a physical propellant. But if we return to a Class D metal fire, the reaction is entirely chemical and much more dangerous. When a metal is burning at 5,000 degrees, water's high latent heat of vaporization is rendered entirely useless. It cannot cool the metal down. The extreme thermal energy actually breaks the covalent bonds of the H2O molecule. The water undergoes thermochemical dissociation, separating into elemental oxygen and hydrogen gas. By applying water, the responder is now actively feeding the fire with a pure oxidizer and a highly explosive fuel. In specific industrial environments, molten aluminum can react with carbon residues and water to rapidly produce methane gas. Applying water to a burning metal weaponizes the molecule itself, turning a standard extinguishing agent into rocket fuel. If water fails, logical safety procedures dictate smothering the fire with an inert gas like carbon dioxide to cut off the oxygen supply. This introduces the inerting paradox. At the extreme temperatures of a metal fire, carbon dioxide and nitrogen are not chemically stable. Highly reactive metals like magnesium will chemically strip the oxygen directly from a carbon dioxide molecule to sustain their own combustion, leaving only carbon residue behind. Titanium is so reactive it will even break apart and burn in a pure nitrogen atmosphere. Official hazardous materials advisories strictly warn against relying on standard sprinkler systems in industrial machine shops that process these metals. Applying incompatible agents to a reactive fire leaves behind a flooded, highly toxic, and chemically volatile hazard zone. Because extreme heat dictates chemical stability, both cooling liquids and standard smothering gases fail completely against a Class D hazard. Controlling a combustible metal fire requires engineered solutions, specifically specialized Class D dry powders. You cannot use a standard ABC dry chemical extinguisher. Those agents contain chemical compounds that will react directly with the burning metal. Instead, specialized agents like MET-LX use a sodium chloride base. When applied, the salt melts over the burning surface to form a thick, solidifying crust. The salt physically smothers the metal, while an added polymer creates a heat-resistant seal that strictly excludes ambient oxygen. For highly reactive alkali metals, graphite-based agents like Lithex are deployed. The graphite conducts heat away from the burning mass, lowering its temperature below the ignition point. These agents succeed because their specific physical mechanisms decouple the fuel from its environment without introducing any reactive molecules. For environmental health and safety managers, understanding this chemistry directly dictates everyday workplace protocols. Facilities must identify every combustible metal risk and establish strict no-water zones long before an ignition event occurs. In many cases, the required protocol is counterintuitive. Isolate the area and allow the metal fire to completely burn out without applying any suppression agent. Ignoring the mechanics of thermodynamics turns a standard fire response into a force multiplier for disaster. Applying the principles of fire science prevents a minor incident from escalating into a catastrophic facility failure. If you want to learn more about workplace safety, fire science, and OSHA rules, subscribe to the HSE Study YouTube channel.